Today we're going to take a look at lines and circles. First, we're going to have to learn a few terms. So let's start out with a chord. A chord is a segment that has endpoints on the circle. So you can see here that AP is a chord. So we have AP is a chord. The next term we'll have is secant. A secant is a line that intersects a circle in 2 points. So here we have line AP is a secant. It intersects the circle at A and P, and it is a line that continues on forever. Then we have a tangent. A tangent is a line in the same plane as the circle that intersects the circle in exactly 1 point. I could extend PT here, make it be that line, and it intersects just at that 1 point on that circle. If it does do that, if it does that, it is a tangent. So it intersects at 1 point on the circle. The point of tangency is the point at which the tangent and the circle meet. So T right there is our point of tangency. We also should know what a congruent circle is. Congruent circles have the same radius. So if the radii are congruent, then the circle is congruent. We also have the word concentric. Concentric circles share the same center, but their radii are not the same. The radius for this one is there, and this radius is bigger. So they share the same center, but they do not have the same radius for concentric circles. Then we can have tangent circles. Circles can be externally tangent, or they can be internally tangent. So external means that the circles are outside of each other and they meet at one single point. Tangent means one single point. Internally tangent circles means that one circle is inside the other circle and they meet with that circle being inside the other circle. We have a couple of theorems too. The first theorem, and there's no names for these theorems, we just kind of go with what they say, and we can abbreviate as long as we don't lose the meaning of the theorem. Remember that. So if a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. So we have this line right here, that is the tangent. And it meets, the point of tangency is the same place that the radius is meeting the circle. When that happens, when the point of tangency and the radius, if the tangent and the radius meet at that point of tangency, then we know we have a right angle. Okay? So if a tangent and a radius meet at the point of tangency, then we have a right angle. Here's another corollary to that. If we have 2 tangents to a circle from a point outside the circle, then those 2 tangents are congruent. So that means if I have this one single point outside the circle and I'm going to a point of tangency onto the circle, that this distance and this distance are going to be the same. And I bet we have a proof of that in the homework, or we'll look at that in our next exercise. So anyway, so tangents to a circle from a point outside the circle are congruent. Then we have this theorem. This one's a converse. It is a converse. If a line in the plane of the circle is perpendicular to the radius at its outer endpoint, then the line is tangent to the circle. This is the converse of that first theorem. So if we know that the line is perpendicular to the radius at the outer endpoint of the radius. So see, here's the outer endpoint of the radius. Then we know that that line is tangent to the circle if they meet perpendicularly. So if a line in the plane of the circle is perpendicular to a radius at its outer endpoint, so if we know this is perpendicular, then we know that is a tangent. So it's the converse of that first theorem. Okay, let's do some problems working with that. So I want you guys to think about this for a minute. I'll read it to you and set it up for you, and I want you guys to work it. Segment RT is a tangent to circle O. If OR is 6 and RT equals 8, then OT equals what? So let's think. What do I know? If RT is a tangent to the circle, and we can see that OR is a radius because it goes from the center to the edge of the circle, RT hits the circle at the end point of that radius, right? So that means I know I have a right triangle. So if RT is 8 and OR is 6, then what can I use to solve the triangle? Remember, if you want to try these by yourself, just turn it off and give it a try and see if you get the same thing I get when you turn it back on. So here I'm going to go 8 squared plus 6 squared equals OT squared. So that is 64 plus 36. So that is 100 equals OT squared. So OT equals 10. Fair enough, right? All right, let's look at the next one. So for this one, segment RT is a tangent to circle O. If the measure of OTR is 45 and OT is 4, then what is RT? So again, I know that RT is tangent, and I see that I have OR, this radius that is also hits the edge of the circle at R. So that means that I know that those two lines are tangent, that TR and OR are tangent. So I'm going to connect this, and I'm going to take a look at OTR is 45. That's what we were told. I'm going to make that. So OTR is 45 degrees. So if OTR is 45, and that's a right triangle, then I know that this is also 45. So, and I know that OT is 4. Again, turn it off if you want to try it yourself. So now I'm going to go back and I'm going to think about my 45, 45, 90 triangle relations. Because see here I know my hypotenuse, and I'm looking for RT, which is one of my legs. So that means I'm going from big to small, so I'm going to divide by radical 2. So I've got 4 divided by radical 2. Remember, when you have something divided by a radical, you want to rationalize that. So I get 4 radical 2 over 2, which is reduce it to radical 2. You guys need to remember to reduce and simplify. Okay, so that's how we do something like that. Here's a few more definitions. We have a common tangent is a line that is tangent to each of 2 coplanar circles. So let's just draw 2 circles. So I got this circle and that circle. Okay. A common tangent means it's a line that's tangent to both circles. So this would be a common tangent. This would be a common tangent. I could also come inside and draw that tangent. I could also come inside there and draw that tangent. So, and it talks about external and internal tangents. A common internal tangent intersects the segment joining the centers. So look, if I put, let me do a different color. If I did a segment joining the centers of the circles, you can see that this tangent and that tangent are common internal tangents because they intersect that line. So that means that this tangent and this tangent are common external. So those are external tangents and these are internal tangents because they cross that segment joint in the centers. So common external tangents do not intersect the segments joining the center. So we have the segment joining the center. So here's the center, here's the center. That is the segment joining the centers of the circles. So the common external tangents do not intersect. So we have one right here and one right here. Those are external tangents. We can have different types of circles doing different types of things also, and that will affect how many common internal and external tangents we can have. For example, if I have two circles that touch like that, I will have my, whoops, that didn't quite work, but you get the idea. I'll have my common external tangents, and then I'll have one common internal tangent there that hits them both right there where they meet. Then I could have the situation where the circles overlap, in which case I'll have my external tangents, but I won't have any internal tangents. Then I have the last circumstance that could happen is where I have the two circles that are internally tangent circles, and they have one external tangent right like that. So as you saw what I did when I was talking about the external internal tangent lines to circles, I can have circles that are actually tangent to each other. And these two circles here are externally tangent because they are outside of each other. And they have this one point of tangency right here. These two circles are internally tangent because one circle's inside the other, and they have a point of tangency right there. All right, so here we are. Here's a problem for us to work on. So we have two circles. They are internally tangent. They have two tangent lines coming from R. One is tangent to circle N at point S. The other one is tangent to circle N at point P. So we want to take a look at these, and we want to find certain pieces of information. So the first one we want to find is PM. So PM is this line right here. So looking at PM, I see that it's the radius of circle M. And if I extend that a little bit further, I see that it is the diameter I can form, and that the diameter of circle M is the radius of circle N. And I'm told that circle N has a diameter of 16. So that means that the radius here is going to be 8. So that means that PM is going to be 4. And guys, if you guys want to work on this yourself, again, pause the video, give it a try, and come back and see how you do. All right, the next one we're looking for is MQ. So see MQ right here is this line. And what I know, remember from my theorems, is that a radius to a tangent is a right angle. So I know that that's a right triangle. And I know that I'm looking for PQ, and um, so we know PQ is 3. So I have a right triangle. I can use Pythagorean relations. I can say that's 3 squared plus 4 squared equals MQ squared. So that's going to be 25 equals mq squared. So mq equals 5. So there we have 5. The next thing we're looking for is PR. I know that RQ is 12. They told me that. I should mark that. So then I know that PR, that's an easy one, is 15. The next one we're looking for is SR. And here's the thing, we have that theorem that states if you have two tangents from the same outside point to the same circle, then they're congruent. So I know that SR also has to be 15. The next thing I'm looking for is NS. So looking for NS, that line right there, well, that's the radius of circle N. And I know that the diameter of N is 16, so I know NS is 8. The next thing that we're looking for is NR. That is that line right there. All right, I've got to remember, where's my right angle? My right angle is right here because it's where the tangent and the radius meet at the point of tangency. That's my right angle. I know that NS is 8. I know that RS is 15. So I can use my Pythagorean relations again, where I get 15 squared plus 8 squared equals NR squared. So 225 plus 64 is 289, which is 17. So that gives me a 17 for NR. And here's the last one. This one's a proof. Okay? And it's not too bad. It's not a bad proof. So we've got that RS and TU are common internal tangents to circle O and circle P. And we were trying to prove that RS equals TU. So first, we're going to do this as a 2-column proof. So I've got my statement and my reasons. So I've got my given that RS and TU are common tangents to circle MP and circle O. And I use that little symbol, like with the O with a dot in it, to stand for circle. All right, so then my second step, the next thing I'm going to do is, see I've got V here, and V is a point outside both circles. So, but VT and VR are tangents to circle O from a common external point, so they're congruent. So I could say that RV is congruent to VT, and I can also say that UV is congruent to VS, and that is because tangents from a common, sorry, that's so messy, common external point are congruent. Okay, that's one of those theorems that we had today. So the next thing I'm going to do is I'm going to do a little bit, I'm trying to get to RS and TU, so I'm going to do a little segment addition. And I'm going to say that RV plus VS equals RS, and UV plus, wait, that's not what I'm saying. Hold on. Let me restart. RV plus VS is RS. So UV plus, okay, that's right, VT equals TU. All right. So that would be segment addition postulate. Then I'm going to do a little substitution thing where, because I know RV equals RV equals VT, and I know UV equals VS. So I'm going to say that RV plus VS equals TU. And I can say that by substitution. That allows me for my fifth step for my fifth step to say then that RS equals TU, again by substitution. So if you can see what I did there, and that's what we got. So that's all I've got for you on this today. We'll come back to class and we'll do a few more examples to prepare you for your homework tonight. See you later. Thank you. All right, so for this one, we have two circles. They are not touching each other, but they do have two tangents drawn to them, RS and TU, and those tangents are internal tangents because they cross that middle line between the centers. So they're internal tangents, and we are trying to prove that RS equals TU. So we're trying to prove that those segments of the tangent, so from point of tangency to point of tangency, we're trying to prove that those two are congruent. So we're going to do a two-column proof for this one. So we'll have our statements and reasons. And we'll start out with our given information that RS and TU are to circle O and circle P. And that is given. So one thing, so again, if you want to try to work through this on your own, do that and come back and see how you did. But so the first thing that I see is that I have this point outside the circles, V. And we have the theorem that says from a point outside the circle, the tangents to the circle to the front are congruent. So I know that I could use that theorem to say that RV is congruent to TV, and the same theorem to say that UV is congruent to SV. And so that's just from a point outside the circle, tangents are congruent. So I've got that one. And then I'm going to use segment addition postulate. So before I can use segment addition postulate, I have to say that these are equal. So I say that RB equals TB and UV equals SB. And remember, that's just the definition of congruency. And now I can use my segment addition postulate to say RV plus VS equals RS, and TV plus VU equals TU. And that is segment addition postulate. Now I'm going to use a little bit of substitution to say that RV, because RV and TV are equal, plus VS equals TU. So basically what I did is I substituted RV for TV and VS for VU and kept it equal to TU, which I can do by substitution. And now, by transitive, I've got that those are equal to RS and equal to TU, so RS equals TU by transitive. Or you could also say substitution. All right, and that's all we have for that. If you have questions, you can come in and ask them. We're going to talk about these in class, see if that's enough to get you through the homework, and we will discuss it in class. Thank you.